Okay, applied optimization. Let's talk about this for a few minutes so we can make fun of Mr. Jansen. Okay, Friday, we looked at optimization from an AP perspective that was not applied, right? So we talked about just getting a function, minimum, maximum, all that optimization talk without the applied part, okay? Today we're just putting it in a word problem, right? So basically taking all the calculus, which you all know pretty well, and making it something you can actually use in a manufacturing plant or in building roads or stuff like that, all right? So let's just dive right in. And design, this is actually something that they really do. A cylindrical can with volume 900 cubic centimeters. That'd be 0.9 liters if you're keeping track of that way. Put it in centimeters because that's what the measurements of the can are built in, right? And minimum let's reword that, using the minimum amount of material possible. Okay. Seems easy. Right. Okay, so what do we got here? We've got Pepsi trying to make some can that's this size, because that's what they want to distribute, but we are trying to use the least amount of material so they minimize cost, right? So let's say you save 2 cents on every can of soda you sell, and let's say you make 100 million sodas a year. How much money are you going to save? Even if it's just 2 cents per times 100 million, that's a lot of money, right? Like $2 million. So very important when you're in such big volumes like that. The key is to identify the shape. Okay, so we want to identify the shape. And we want to identify the two formulas. Will be proper in our language, two formulae that we're going to use. Okay, so what two cylinder formulas do we have here? Volume. That's obvious, right? So volume equals what? You know what to write down here. Pi r squared h. Okay. What else? How would we? Yeah, surface area. That's 2 circles plus diameter times height. Okay.
Wait, just the diameter?
Yeah.
So do you need the pi?
You only need the
Diameter is 2 pi r. So, do you know why this is
diameter isn't 2 pi.
how it is?
But that's circumference.
Or sorry, circumference.
Oh,
Okay.
okay.
Yeah, I misspoke. That's probably where you got messed up, so I'll just stop right there. Okay. Okay, which of these numbers do you have available? Volume, right? So let's, at this point, you just go with what you have, right? So plug 900 in. and solve for one of the two variables. Okay. So solve for, let's solve for h since it's not a nasty square. Okay. So h equals 900 over pi r squared, right? So with this equation, I think it's called the constraint equation if you want the word. We are solving for one variable. Okay? That's the key on that one. So you're given some information, use it to solve for a variable. Okay? You good so far? Now, we have to use that to get rid of an h. We're in the this is our minimization equation, right? Or what we call optimization equation. We're going to actually calculate the derivative. And derivatives aren't very fun when we have more than one variable, right? So we're going to get rid of it, the h, right? So let's rewrite surface area. Nope, just erase it. Pi r squared. Okay. Are you good with that substitution? And now simplify it. So surface area is 2 pi r squared plus 1800 over r. Yeah. Good? Okay. So, what do we do with that equation now? Yeah, your derivative, because we are doing just a minimum, right? So you just think in terms of regular functions, you just calculate the derivative. And then we'll do a sign analysis. Right, do calculate derivative, set equal to r, do a sign analysis, we'll see where the minimum is. Okay, so you could write it this way if you want, SA prime. Sometimes you'll see it written derivative SA over dr, right? Because r is the variable we're differentiating. Right? Whatever. Okay, I think that's right. And these are the extended page problems we know and love. Okay. You good with that derivative, right? Exponent power rule. All right, set equal to 0. Solve. Use your algebra skills. Oh, I failed as a math teacher. Remember when you get a variable top, bottom in two different spots, you can just add it over. Now multiply by r squared. So we're going to 4 pi r cubed equals 1800. Right? So r cubed is, this is where decimals are okay because we're in a real world context. Okay. Just remember to carry that decimal out quite a ways for now. Right? Huh?
What is that in fraction form?
1800 over 4 pi. Right? Does anybody have that number? David, I'm going to kindly assume you're on a calculator.
Yes,
Okay. Thank you. Does anybody have this number? 1,800 over 4 pi? One 143.23944. Okay, and then cube root is 5.323. Okay, that's probably going to be our minimum. It's the only one we found, right? If you need to check, you can do a site analysis. And then use the derivative. Or, sorry, SA prime at 5. SA prime at 6. And you will find
So the least amount that we can use for one can is 5.3 centimeters.
the radius.
That's the radius.
Yeah, so radius of the can, 5.323. Okay, so,
So that's like what it means in context of the problem, so the
Yeah.
radius is 5.32.
yeah, and then how would I calculate the height of the can? Right here. Yeah, so plug that in there and find H. Okay.
So, when you scroll up,
This would be 10.46.
so is that all you have to do is the R and H, because that's the minimum amount of material?
That tells you how big the can is. Oh. No, the surface area of the can is determined by the radius and the height. Once you've minimized those, you know that, well, you've minimized the surface area, you use the radius and height to build your cans. So in the manufacturing plant, they don't put surface area in the computer, they actually put the radius or the diameter, whichever their program allows for, and the height. That's how things work. Okay, so we don't even have to worry about calculating that number. You can, but what's the point? I mean, you can figure out how much it costs probably with the surface area or something like that, but there you go. So, are we good there? Say what? If you're an American, that can's about 2 inches in radius, so it's 4 inches in diameter, right? And it's about, wait, hold on a sec. Yeah, and then it's about 4 inches tall as well. So it's like short and stocky.
Yeah, we'll buy that. I think we'll buy that.
Okay, do you want another one? A little harder, maybe? Or you just want to let me give you the homework and work on it? There's a problem about minimizing travel time. There's a problem about optimal prices. And there's a problem that deals with the problem that has no solution, which is fantastic. You just want to be done. Yeah, is that the best thing for us? It's only a point. No opinions any other way. We've got one vote. Okay, fine. Be that way. you're witnessing this is the one time I'm doing what I think is not best for you. Record it down in history. It's time stamped on YouTube, so don't worry about that.
Did your class 2 years ago, were they like us at all?
Yeah, pretty much. It's very, you are mirroring them.
Oh, that's good.
Yeah. So 3 through 70, clearly, and 23 and 41. That's 7 odd, by the way. Okay, so I've given you no evens. You can check your answers. It's very obvious if you don't show the work that you have no idea what you're doing. And then some AP problems. Part of the key to these is being nice and organized. So write the equations out. Do not be afraid to use paper.
And then Danielle, fine.
The tree's already dead. And with that, we will sign.